Good afternoon, everybody. I'm Pierre Fortin, JP, from the Hawthorne and the Scots Canada technical team. So, as you noticed, I'm French Canadian, so forget me if I say four instead of on instead of two, and I use the wrong past tense. So, hopefully, you will be still enjoying the presentation. Today, we're going to make a relationship between the previous talk, what Greg said about soil analysis and water analysis, and we will look at how we look at the behavior of the water and the nutrition solution between the different mixes that are commonly used in cannabis production, in order to understand what kind of analysis is best for you to follow your crop. So we're going to talk about the big three substrate: Rockwool, peat mixes, and core mixes, and highlight, I would say, the differences between those three mixes. And at the very latest, we'll get a touch on feed solutions and feed programs. We, as a grower, we know, I would say, the main characteristics of each of the substrate. Things like porosity, water retention, drainage, but we usually don't know what's happening to the water and the nutrient solution between a wet and a dry cycle. So what's happening during the dry back? What's happening when we wet back the substrate? These are the kind of things that we are going to look at today. And to do that, Hawthorne use a analysis technique that is called the moisture retention curve, in order to get a little bit deeper into the water behavior within each of the substrate. So this is a moisture retention curve of I would say, a particular mix. This curve show I would say, the amount of volume, the amount of water contained in the substrate relative to the water status within the mix. So on the y-axis, on your left of the graph, we have the volumetric water content. So we said volumetric water content because it's a percentage of the volume of the soil or the media that is filled up with water. For example, a 1 gallon pot filled up with core or peat mixes, if the volumetric water content is 50%, it will mean that half of that gallon is filled up with water. So within that substrate volume of 1 gallon, half a gallon is water at 50% volumetric water content. And the scale of the y-axis usually range from 0 to 100%, and 100% will correspond to the total volume of the soil, and not really the volume of the pot or the container used, but the volume of the soil within that pot or within that cube or container. The x-axis represent the status of the water, and to do so, we measure actually the metric potential of the soil. You'll notice that the metric potential is negative. If you could look down at the units beside metric potentials, is minus kPa. So minus kPa is a pressure measurement. To give you an idea, 10 kPa, 10 kilopascal, equals to 1.4 psi. So it's really a pressure measurement. We measure the pressure within the soil at different moisture content. To do so, we use a simple tensiometer, and there's different type of tension meters. It's actually a rod of liquid which is connected to the soil through a ceramic cup. And as the soil dries out, as the water is pulled out from the soil, there's a vacuum pressure created, and that can be registered within a very simple pressure gauge there. There's more sophisticated equipment, which is more like electronic, but both either devices doing the same thing. So what's happening in the soil as the water, as the soil is drying out, or as the plant is picking up water and the soil dries out, the water is more and more tightly retained by the soil particles. And that, I would say, retention force is measured by this pressure gauge. What we have to understand here is that since we're talking negative values, minus 1 is when the soil is full of water, or 0 will be when the soil is fully saturated. And as we go down the scale to minus 2, 3, minus 4, 6, 7, the water is more and more tightly retained by the soil and more difficult to be absorbed by the roots. So imagine that that the roots must apply the same amount of pressure to absorb that water. So at minus 1, which is a higher mature potential because we're negative 1 on the left side of the scale, the water is pretty freely available in the water, probably contained within large pores of the soil, and the roots can easily absorb that water. But as we go down the scale to lower mature potential, minus 8, 9, 10, the roots has to apply with using different mechanisms, must apply the same amount of force, the same amount of work as minus 10 kilopascal to be able to absorb that water. The top portion of the curve constitute the solid matter of the media. So it's either, I would say, Rockwool fiber, the mineral fibers, peat moss, core fibers, perlite, vermiculite, those kind of things. So the top portion of the curve above the intersect with the y-axis is the solid matter of the media. That doesn't change, unless the soil gets compacted. In the meantime, that's a stable value. The lower portion of the curve represents the volume of the media that is filled up with water. So as we dry down, you see that the curve is going down, and as we go towards minus 10, there's less and less water available into the media. The top portion of the curve represents the aeration. So as the water dries down, there's more and more air in the media. So when the water is picked up by the roots, or when the soil or the media dry by evaporation, the pores that are filled up with water are slowly replaced with air. So as the soil dries out, the media dries out, aeration goes up into the media. The bottom portion of the curve at minus 10 kilopascal, scientists declare that water to be non-available, or I would say slightly available. This is because that at pressure, the water is so tightly retained by the media particles that it is very difficult for the roots to absorb that water, or that water will be absorbed very slowly. So we call that portion of the curve non-available water. So it's not true that the water is not really available, but as I said, the pressure to the force to apply to absorb the water is so great that the rate at which the plant will absorb water will be very slow. So since the plant cannot absorb as much water as it would need, then there'll be a phenomenon where stomata will start to close to the plant to protect themselves again wilting. And as the stomata close, there's less and less CO2 absorbed by the plant, thus less photosynthetic activity. So that area of the curve, below minus 10 kilopascal, the water that will serve there will serve just to maintain the metabolic state of the plant, but will not be used for active growth. In terms for you to understand a little bit better, wilting will happen around minus 25, minus 35 kilopascal. So between 10 and 25 to 35 kilopascal, the plant will just maintain its metabolism and will dry out, I would say, as a lower metric potential. And the wilting point will depend on many factors, like the size of the plant, the size of the container, how much media available to the roots, temperature, VPD, this kind of thing. So for a very small plant in a very large pot with a low VPD, the plant will sustain a little bit, I would say, longer before wilting. But a very large plant in a small container at 80 degrees with a good VPD, the plant will not sustain as long, and wilting will occur a little bit earlier down the curve. One of the last point I want to talk to is the intersect of the curve with the y-axis. That point there is called the saturation point. This is when all the pores of the substrate are filled up with water. The only way for us to do that is to plunge really the media into water to make sure that all the pores are totally saturated. So this is total porosity, which is I would say, a theoretical value, because as soon as we let the media drain freely, we'll come down to a point called container capacity or pot capacity, or in the field that may be called field capacity. This is the point where the maximum water is absorbed by the media under free drainage. So if we start from total porosity and let the soil drain freely, there's a portion of the pores that will be emptied. There's a portion of the water that will be drained out by gravity, and these pores that were originally filled up with water will be replaced by air. So container capacity is important because this is the maximum water retention of the media, and also we can also know how much air is within that media at container capacity. And just also consider that any watering beyond container capacity will result in runoff. On that slide, you see that the big three media behave very differently in terms of water retention. With Rockwool, we can see that on the intersect with the y-axis on the left of the graph, that total porosity is very high. And as we see the curve going down up to a minus 3 kilopascal, we can see that most of the water is available to the plant, which is a large part of the media volume. From minus 3 to minus 10, you see that we're down to a flat curve, meaning that there's in that substrate, there's absolutely no buffer. So when all the available water is used, the plant will be subjected to wilting very, very fast. The container capacity of Rockwool is near 0.75 kilopascal. If you look at the upper portion of the curve, the difference between the intersect and 0.7 give us roughly 10%, 11% aeration at container capacity for a 6 by 6 by 6 inches cube of Rockwool. With core, we see that core with the intersect, the red curve, core has a very high porosity too, a bit similarly like Rockwool. But if we look at minus 10 kilopascal, not all the water is available for plant growth. So core has a little buffer where water is absorbed by the fiber, and I would say less available for plant growth, or non-available for active plant growth. Still, core has a very high availability of water, and the container capacity of core will be more or less in the area of 1 kilopascal. And we can already notice that at 1 kilopascal, core, indicated by the red curve, has much more have much more aeration than Rockwool at container capacity. Peat moss, we can really see that peat moss has a lower porosity than the two other substrate, but has a very greater buffer. So this is the particularity, the main characteristic of peat moss: a large buffer. And I would like to say that that buffer is also a reservoir for nutrients. And because of the organic nature of peat and core fiber, some of the nutrient can be tied up within that buffer. The container capacity of peat moss is around 1.5 to 2 kilopascal, depending on the substrate, and the aeration is less than core at pot capacity. I'd just like to mention that those three curves are, I would say, averages in the market, but we have seen in the past core that has very short fibers or very dusty, that has much less aeration than that curve. And also on the opposite, we've seen very coarse peat moss that has a very great aeration at container capacity. So just consider those three curves as general, I would say, indication for the purpose of the talk today. Now let's take a closer look at Rockwool. So as we said, Rockwool has a very low buffer. So most of the water in the Rockwool cube is retained by capillarity. And because of the nature of the fiber, because the way the fiber is woven, that retaining the water retention capacity is very high. I like to compare Rockwool like true hydroponic, where plants are sitting in water. Actually, because Rockwool has a high water retention capacity, and because Rockwool has virtually no buffer, we can say that this system is kind of a perch hydroponic. So it's really close to a true hydroponic, with the exception that the water is suspended within a block instead of flowing into a bucket or a trough. What does it mean in terms of irrigation? It means that, as I said, the water will be suspended in the block and be almost totally available for plant growth. So unless more water is applied to induce a runoff, the water will be, I'd say, suspended in the block, totally available. In terms of nutrition, what does it mean? It means that water is the carrier for nutrition. So if the water is available, then the nutrient will be also available. So because of the nature of core that retains a lot of water, usually irrigation will be sparingly done during the day, following more or less the pattern that appears on the bottom left of the slide. So because core does have a very high aeration, I would say in the area of 10%, the dry it back will allow the cubes to absorb more oxygen for the roots. So in Rockwool, we cannot maintain container capacity all the time because there will not be enough oxygen for the roots. So we'll be in a oxygen stress. So that's why usually we observe a dry back at night and a reweighting, I would say, reweighting schedule during the day up to reaching a plateau. So by doing this, we kind of create an artificial buffer because we never let dry down the soil totally. And we also create I would say, a reserve of oxygen necessary for a root's metabolism. And in terms of analysis and nutrition, what we can say is because we're kind of a true hydroponic, the feed solution should really reflect what's in the cube if runoff is high enough. So if we apply a sufficient amount of runoff at each watering, the nutrition, the composition of the nutrients within the block will be very similar to the original feed solution. Actually, the nutrition strategy here is to maintain within the block the original nutrient composition and the original ratio as much as possible. Because, as I said, the roots are battling in suspended hydroponic system. So, because of the watering scheduling, and because of the dryback that we have to impose to Rockwool, one may analyze what's in the block, but sometimes it does not reflect what's in the leaf actually. So the plants will pick up their nutrients, and that will be reflected in the leaf analysis. So we've seen in situation where running off is, I would say, between 10 and 20%. We've seen situation where the nutrients in the block are a little bit different than what's in the leaf. This is if a leaf analysis is very nice in terms of NPK, sometimes we may observe like low N into the block and I, P, and K because they are not they are accumulating because they're not I would say absorbed at the same rate. So analyzing the block is very interesting to look at pH and also to look at EC to make sure that during the dryback, EC doesn't rise up too much. But really, the leaf analysis, I would say, is the main indicator in that situation. As we said, peat mixes has a very high water retention capacity because of the peat fiber. So it's not uncommon in a peat mix to have 60% water retention. But peat has a very large buffer, as indicated by the gray bar on the right hand graph. And that water will be either absorbed by capillarity within the between the peat fiber, or be absorbed by the fiber within the fiber, because sphagnum moss is very spongy in nature and will absorb a lot of water within their pores. And because also of the organic nature of sphagnum moss, the surface of the organic matter are usually charged negatively, which will act like a magnet to absorb water and water molecules, but also nutrients. And this is what we call cation exchange capacity, as demonstrated by the little figure on the left of the peat mix. So we couple of interesting things here to notice. Okay, because of that buffer, because of that cation exchange capacity, some of the minerals, and also because peat moss is very poor, some of the minerals from your feed solution will be absorbed by those fiber, as well as water be absorbed by the fiber for the first watering. So peat moss on the first watering act as a sink. And if the peat mix is not, I would say, fully, totally charged with nutrients to start with, it's not uncommon to see that the first watering gets absorbed, the nutrient get absorbed by the peat fiber, and the EC is being very low in the peat moss, despite the fact that we water with a fairly high EC nutrient solution. To combat that phenomenon, we do recommend to either buy a mix which is pre-charged with a nutrient charge, or to wet the mix with a nutrient solution instead of using clear water. So that will make that I would say that absorption to take place without impairing too much nutrient composition of within the available water. Second thing, because of that buffer, okay, although peat can absorb 60% by volume of water, the buffer may represent 35% of the volume of the volumetric water content. So because of that buffer, we're really using only, I would say, 20, 25, or 30% of available water for active growth. And if we like to maintain, because of the nature of the peat mix that is used, because we have maybe to maintain that mix a little bit drier, to put a little bit more air in the mix, the available water may represent only 20 to 25% of the total water retention capacity. In practice, what it means is that the watering of a peat mix is not related to the full retention capacity. We will be working with only 20-25% of the size of the pot, of the volume of the pot, in terms of available water for active growth. And this is the same thing with the nutrients. Because we are working with a smaller volume of water to feed the plant, nutrients will be a little bit more concentrated within that smaller volume. So usually, in terms of nutrition, we'll be working with slightly higher ECs compared to Rockwool in order to provide enough nutrient to the plant. In terms of analysis, in terms of feeding, remember that in Rockwool, the objective was to maintain a specific or inadequate concentration within the block. With peat moss, because peat moss has a so high water retention capacity and because the buffer is high, we are more thinking in terms of how much nutrient I have to apply to my plant between two irrigation events to be able to sustain its growth. So we're not talking here in terms of how many nutrients, what's the concentration of nutrients within the soil, the available soil water, but we're thinking more in terms of how many NPK, how many milligrams or microgram of the NPK I have to apply, I have to provide my plant with in between two watering to sustain its growth. So this is a bit a different minding than Rockwool. So we don't maintain a concentration. I'm insisting on that. We don't maintain a nutrient concentration within the peat moss because we will have to do so much runoff, and it'll be almost impossible for a plant to grow in a wet mix like that. We have to think in terms of the amount, in terms of weight of NPK, Ca, Mg, and the minor elements we need to provide at each watering to sustain the growth. And as the water, as I said, some of the nutrients will be tied up within the cation exchange capacity of the fiber. So what it means in terms of analysis, it means that when we replenish the pot with fresh nutrient solution, the EC will go up. Some of those nutrients will be picked up by the plant. So in theory, EC should go down in between two watering as the plant is picking up nutrients. But the buffer will provide back some nutrients to the soil, to the available portion, the available water portion of the substrate. because there's always an equilibrium that is maintained between what's absorbed by the cation exchange capacity and what's available in the water. So in practice, the nutrient solution within the pot, the available NPK within the pot is in constant motion. So it is difficult to rely only on soil analysis to make sure that our plant is fully provided with nutrients, because the available water salt solution is constantly changing. Uh, we've seen analysis where the leaf, in terms of leaf analysis, was within the spec range for cannabis. And in soil, I've seen analysis that may range from 10 ppm of nitrogen up to 100 ppm of nitrogen for a same leaf analysis. So um, again, to analyze the soil, it's difficult because first we don't know when to really take the sample out. Is it just after watering? Is it just before watering? Is this in the middle of the day? Uh, and it's difficult to really make a correlation between, I would say, plant health and soil analysis. Um, uh, However, soil analysis is good again to check if there's not like a big nutrient imbalance, or if the EC is rising or going down, and also to check the pH. So in a peat mix, I would say, system, if EC is going up, it's because our original feed solution may be a little bit too strong. And if EC is constantly going down, and we've got, let's say, deficiency results on the leaf analysis, is because our feed solution is too weak. As we say, core fiber as a buffer, a little bit like peat moss, but I would say a shorter buffer than peat moss. So the general irrigation of core and nutrition of core will behave more or less similarly than peat moss. However, core fiber are naturally charged with elements, namely potassium, sodium, and chlorine. So during the first watering, um, instead of as peat moss acting as a sink, core fiber will exchange mineral with the fertilizer solution. So this is why companies like Hawthorne do are buffering the core usually before packaging. This is to force that exchange phenomenon before drying out the core and packaging it out for your use. So what we do, we wet the core with a nutrient solution so that the exchange can take place between the available water and between the nutrients tied up in the cation exchange capacity of the fiber. And the core is then leached out again. So that important factor, and you probably know that it's preferable to get a buffered core. However, in the market, there's no standard for the buffering. So it's important for you to really get an analysis of your core to see if the amount of chlorine and sodium in the available salt solution is too high for your growth, or if you need to do some more buffering. So buffering or leaching the core is easier to do it with a nutrient solution so that the exchange can take place. And what we do recommend is to use a mild nutrient solution or strictly a veg nutrient solution with the core to container capacity, wait for 24 to 48 hours, Leach it again, maybe with the same solution or a weaker solution to get the chlorine and the sodium out as much as possible. So that process, you may have to repeat that process several times. So analysis of the composition of chemical analysis of the core is necessary between each buffering to make sure that we reach a stable amount of chlorine and sodium within the core block. The last point I'd like to talk today is the relationship between the composition of the nutrient solution, so what you have in your day tank or your stock tank, and what's happening in a pot. As we say on Rockwool, the feeding solutions should be or usually very close as much as possible of what's in the block compare what's is into your feed solution. With core or peat moss, since there's a fairly large buffer and a fairly large absorption, I would say, capacity of these medias, the feeding is more in terms of how many milligrams we do apply between each watering, and is these milligrams of NPK are enough to sustain a very active growth between each two watering events. One thing, however, that we have to look at is depending on the amount of water that we do provide to those, let's say, media, will affect the real amount of nutrient that will be captured by the pot. In that example here, we've got a nutrient solution as indicated by the central column, composed of 150 ppm of nitrogen, 80 ppm of phosphorus, and 300 ppm of potassium. We apply it at the rate of 1.5 liters per plant, probably per day, depending on the size of the plant. That will provide to the plant 225 milligrams of nitrogen, 120 milligrams of phosphorus, and 450 milligrams or micrograms, sorry, of potassium to the pot. So the net value is actually a combination of the solution strength, solution concentration, the EC of the feed solution at the beginning, and how much of that water is applied to a pot. So you can see on that graph, if you go down to applying only 1 liter of water to the crop, or half a liter of water to the crop, the net amount of nutrient that will be given to the container is less. So this is something I see very often on the market, where people start with a feeding solution based on a feed chart, but the amount of water applied to the crop is very variable, and this affects the actual amount of nutrient that is available to the plant. So if the watering regime is changed for some reason, either because you want to apply water stress, make sure to adjust the composition of the feeding solution to make sure that the plant will receive the right amount of nutrient at each watering. So to conclude, core, its main characteristic, Rockwool, its main characteristics is that it's a block of free water. Core has a high porosity. Peat has a good aeration. Peat acts as a sink for nutrient under the first watering because of that cation exchange capacity of the fiber. Core must be buffered. No buffering is required on the Rockwool. Irrigation is more on a pulse sequence with Rockwool. With core and peat moss, it's usually a 1 per day kind of watering strategy, or the watering can be split into, I would say, several 2 or 3 watering per day, but usually it's a 1 or 2 every day. Because of the high water retention capacity and the buffer capacity of these substrate. The nutrition strategy is to maintain a certain amount of ppm of the nutrients within the Rockwool, while in core and peat moss, we better think in terms of milligram per day that we do apply to the plant to be able to sustain an active growth. So the takeaway here is water and nutrition management varies between those three medias. And the other takeaway I would say is that leaf analysis is, I would say, the prime test to follow the nutrient status of the crop, the health of the crop, and PC, EC measurements within the media is, I would say, complementary as analysis to make sure we don't undergo into I would say, a toxic accumulation in the soil, or also a depletion of nutrient into the soil, so that we can vary or modify the composition of the feeding solution. Thank you so much for listening to me. I hope this has been been a little bit valuable for you, and feel free to ask questions. We'll answer to the chat. Thanks a lot, and have a nice day.